In the beach sand of Hiroshima Bay, researchers found a tiny glassy droplet created during one of the most destructive events in human history. It looked like an ordinary grain of dark debris. But when scientists placed it beneath an electron microscope and examined its internal structure, they found something that had never been documented before. Hidden inside the droplet was a microscopic crystal containing iron, chromium, nickel, manganese, molybdenum, aluminum, and silicon. These ingredients were not unusual by themselves. Several are common in industrial steel. What was extraordinary was the way their atoms had arranged themselves. The explosion over Hiroshima had accidentally created a previously unknown multi-component alloy. The discovery does not make the atomic bombing a scientific experiment, nor does it reduce the event to an unusual materials process. The destruction of Hiroshima on August 6, 1945, caused immense human suffering and remains a warning about nuclear weapons. But the microscopic debris preserved around the city has also become a physical record of conditions so extreme that they briefly produced forms of matter scientists had never encountered. The central question is how a blast lasting only seconds could mix familiar elements into an entirely new crystal structure, then preserve that structure for more than 80 years. The story begins with objects known as Hiroshimates. These are small, often rounded pieces of glass and fused material recovered from beaches around Hiroshima Bay. Many are only a fraction of a millimeter across. They formed when the atomic explosion heated buildings, vehicles, soil, and other materials to extraordinary temperatures. Concrete, glass, metals, and minerals were shattered, melted, or vaporized. Some of that material rose into the expanding fireball. As it later cooled and fell, droplets solidified into tiny spheres that eventually became mixed with beach sand. At first glance, Hiroshimates can resemble natural volcanic glass or the microscopic particles created when meteorites strike Earth. All three processes involve intense heat followed by rapid cooling, but their chemical contents can reveal the human environment from which they formed. A volcanic droplet begins with molten rock. A meteorite impact mixes planetary minerals. A Hiroshimate can contain fragments from a modern city, steel, concrete, glass, soil, and industrial materials transformed together inside the blast. Researchers examined 34 pieces of Hiroshima fallout debris using several high-resolution techniques. Electron microscopy allowed them to view structures far smaller than anything visible through an ordinary microscope. Chemical analysis identified the elements inside individual grains, while X-ray diffraction revealed how their atoms were organized. Most of the metallic particles were understandable. Some contained iron and chromium in arrangements resembling known industrial alloys. These could have come from stainless steel, machinery, vehicles, or structural materials that were heated during the explosion. Then the researchers reached one unusual grain. It contained a complex mixture dominated by elements commonly associated with steel and high-temperature alloys. But instead of separating into several ordinary phases, the atoms had entered a highly organized crystal structure that had not previously been reported with this composition. A metal is not defined only by which elements it contains. Atomic arrangement matters just as much. Carbon atoms can form soft graphite or extremely hard diamond depending on how they are connected. Steel can become harder, softer, more brittle, or more resistant to heat depending on its microscopic structure. Two materials containing similar ingredients can therefore behave very differently if their atoms solidify into different patterns. The crystal inside the Hiroshimate adopted what researchers described as an ordered structure related to the Al-04 type. That name refers to a known geometric arrangement originally associated with aluminum and gold. But the Hiroshima particle placed several different metals into corresponding atomic positions, while also containing an unusually large amount of silicon. This was not simply a random clump of melted metal. The atoms had organized into a repeating three-dimensional pattern. To understand how that happened, imagine shaking several different shapes inside a container and asking them to form a perfectly repeating wall before the container freezes. Under normal conditions, the pieces may separate into groups or become trapped in disorder. But at a particular temperature, pressure, and cooling rate, they might briefly find an arrangement that would otherwise be extremely difficult to create. The Hiroshima fireball provided exactly that kind of extreme and temporary environment. The blast heated material until some of it became vapor. Metallic atoms that had previously belonged to different objects were mixed inside a turbulent cloud. As the fireball expanded, temperature and pressure fell rapidly. The atoms condensed, collided, and began forming solid particles. The cooling happened so quickly that some structures may have been locked in place before they could transform into more stable and familiar forms. Materials scientists call this kind of structure metastable. It can survive for long periods even though another atomic arrangement would be more stable under ordinary conditions. Glass provides a familiar example. When molten material cools without enough time to form an orderly crystal, its atoms become frozen in a disorganized state. The Hiroshima particle followed a different route. Instead of becoming completely disordered, its atoms crystallized into a highly ordered but unusual configuration. The researchers argue that this particular combination resulted from several factors occurring together: vaporization, chemical mixing, extremely high temperature, and exceptionally fast cooling. That means the alloy was not necessarily present in any building or machine before the explosion. Its ingredients may have originated in several different materials. The blast brought them together and created conditions under which a new structure could form. The microscopic grain is therefore a record of motion. Iron, chromium, and nickel may have come from steel. Molybdenum and manganese could have come from specialized industrial components. Aluminum may have originated in construction materials or equipment. Silicon could have been supplied by glass, concrete, or soil. Inside the fireball, the distinction between those objects disappeared. A window, a steel frame, and a machine component could become part of the same vapor cloud. Their atoms were mixed, condensed, and reorganized into something that had not existed before. However, scientists cannot yet reconstruct the exact journey of every element. The composition provides clues, but it does not identify one specific building or object as the source. The particle records the chemistry of destruction without preserving a complete map of where its ingredients began. The discovery also belongs to a broader scientific category called high-entropy or compositionally complex alloys. Traditional alloys often contain one main metal with smaller quantities of other elements. A compositionally complex alloy can contain several important elements, creating an enormous number of possible atomic arrangements. Researchers study these materials because some combinations show unusual strength, corrosion resistance, or stability at high temperatures. But the existence of an unusual atomic structure does not automatically mean it has useful engineering properties. The Hiroshima crystal is microscopic. Scientists have not produced a large sample, performed mechanical tests, or shown that it would make a superior aircraft, engine, or protective coating. Any technological application remains speculative. Its immediate value is more fundamental. It demonstrates that extreme human-made events can generate mineral and metallic structures outside the known record of conventional manufacturing and natural geology. Scientists have already found other unusual materials at sites shaped by enormous bursts of energy. Trinitite, the glass formed during the first nuclear test in New Mexico, contains melted desert sand and material from the test structure. Similar fused debris has been studied at other nuclear sites. Meteorite impacts and lightning strikes also create brief high-temperature environments. Lightning can fuse sand into branching tubes called fulgurites. Large impacts can produce new minerals through pressures and temperatures rarely found near Earth's surface. Hiroshimates belong to this family of materials created in moments when ordinary conditions collapse. But they are distinct because they preserve the chemistry of an urban landscape exposed to nuclear destruction. That gives them historical value as well as scientific value. Documents and photographs show what happened above the ground. Survivor testimony preserves the human experience. Buildings such as the Hiroshima Peace Memorial remain visible reminders. Microscopic fallout particles preserve another layer of evidence: the physical transformations that occurred inside the fireball and during the material's descent. The newly discovered alloy may help researchers model those processes more accurately. Its structure can constrain estimates of how hot the material became, how completely it vaporized, and how quickly it cooled. Different atomic arrangements form under different conditions, meaning the crystal acts as a miniature thermometer and clock. But reading that clock will require additional experiments. Researchers could attempt to recreate similar compositions in laboratories using furnaces, rapid cooling equipment, or vapor deposition systems. If they reproduce the structure, they may identify the narrow combination of temperature and cooling speed required to form it. That work could reveal whether the material was an extraordinarily rare accident or a predictable result of a particular physical pathway. Scientists might also re-examine fallout from other nuclear explosions to see whether similar structures formed elsewhere but remained unnoticed. There may be many more unknown materials hiding inside previously collected samples. The unusual alloy was found in one microscopic grain among dozens of pieces. Earlier instruments may not have had the spatial resolution needed to separate it from the material around it. This illustrates an important pattern in science. A sample does not stop containing information simply because it has already been studied. New instruments can return to old material and reveal structures that previous generations could not detect. The Hiroshima had rested in sand for decades. The alloy was already there, but the ability to recognize it arrived much later. Still, the discovery must be discussed carefully. Describing the alloy as a scientific curiosity cannot separate it from the circumstances of its creation. It exists because a city, its infrastructure, and countless human lives were exposed to a nuclear weapon. The particle is not merely a new material. It is evidence. At the atomic scale, it preserves a few billionths of a meter of organized structure. At the historical scale, it came from an event that transformed a city and altered the course of the modern world. That contrast is what makes the discovery so unsettling. The crystal is tiny, precise, and highly ordered. The process that created it was catastrophic. More than 80 years later, scientists can examine its atoms and reconstruct part of the fireball's chemistry. Familiar metals entered the blast as components of ordinary human objects. For seconds, they became vapor inside an environment unlike almost anything found naturally at Earth's surface. Then they cooled together and formed a structure science had never recorded. The explosion disappeared almost instantly. The alloy remained. Inside a grain of glass smaller than the tip of a pencil, matter preserved a permanent record of what happened when a city was exposed to unimaginable heat.